Good morning, Ben Cohn. This is my AP Calculus course. Class number 1, looking for limits. So, big picture here, the entire idea of calculus, at least the first half of calculus, is to find the slope of a function. So you've probably heard this before, calculus and slope. So you have a graph, kind of like that. And the idea is we want to find the slope at this point right there. And so, if you think back to your algebra days, which, you never really get out of algebra. Algebra is kind of an integral part of life. You have rise over run. So your thought is, hey, we'll do a little bit of up, we'll do a little bit of sideways, and in the end, we have some sort of slope. We'll call that m. And the idea here is as dy and dx get smaller, then your slope gets more and more accurate. So if we do something kind of like this, what we'll call this? Delta x small, delta y small, this will probably be more accurate than the bigger one because it's closer to the point you're looking at. And the whole idea is, how small can you get it? At some point, well, you're like, well, what if this dx is infinitely small? What if this dy is infinitely small? Does that give us any sort of meaningful answer in life? Does that even exist? Can something even be infinitely small? Well, that's where limits come in. That's the idea of calculus and kind of where we're going. Second half of calculus is basically going backwards. So you sort of take a slope and you make a graph from it. Instead of taking a graph and getting a slope, take a slope and you get a graph. In practice, though, what that comes out to is you have some sort of graph and you're finding the area underneath the graph. And that's the second half of calculus. So, but the first part, though, before we can even really get this rocket launched, so to speak, is we need to resolve this idea of, hey, how do we, if we have these small infinitesimal things, these small delta x's, the small delta y's, how do we turn that into something that makes sense? Is that even possible? Is that some sort of deep philosophical contradiction that brings on an existential crisis and breaks our whole worldview? Well, sort of, maybe. We just kind of assume it doesn't. Example. So, Zenos Paradox. Zeno, Greek, pretty sure Greek, did a handful of paradoxes, and they're basically thought experiments where it's like, all right, that dealt with limits and infinitesimals. So one of them was Achilles and the tortoise. So the idea is you have some guy running, this, call him Achilles, going that way. You have some sort of tortoise. I'm not even sure how you draw a tortoise. Something like this. Whoop. Yeah, that probably should be green, and there should probably be more. There we go. That's a tortoise. And they're both running as much as a tortoise. Oh, does a tortoise run? Does it waddle? I don't know. It's okay. So the idea is, they start running, and we look at the time. We do the first time period. And the first time period is when the tortoise moves from there to here. So the tortoise has covered this distance, while Achilles, some guy, covered this distance. And we'll call this time 1. And so now we're at the situation where we have the person here and the tortoise here. My tortoise are getting less and less artistic. And so now we have this situation. So, to be clear, the first time period was the amount of time it took the person to run where the turtle started. And after this point, the turtle has moved a little bit further away. So now, if we take this time period, and we look at how much time it takes for the person then to get to where the tortoise is now, so we have another situation then, where it's kind of like this. Where we have another picture of the tortoise, move up just a little bit, and this will be T2, then is the amount of time that the person takes to get to where the tortoise now was. And if we kind of zoom in on these, we can basically expand this to look just like the original picture. Long story short, I know this sounds kind of confusing. If we draw this, what we're looking at is we have a guy that starts over here. We have a tortoise that's over here, and we keep dividing these into smaller and smaller segments. Now these segments get infinitely smaller, but there's an infinitely large number of these segments. So we have T1 is where the man catches up to where the tortoise is started. Then we'll have T2. We'll add these together. And that's where the tortoise was after the man finally caught up to the tortoise's initial position. And then we do something similar again where the man then catches up to a tortoise was the next time. And we keep going on. And the idea is we can make this on forever until we have an infinite number of these time segments. And you're like, well, this sounds ridiculous. I start running, the tortoise starts running. Eventually I'll catch up to him and then pass him. True. And that's why this paradox is so good, is because like you look at this and you're like, yeah, it's obvious that a man can run faster than a tortoise, that he can catch up to a tortoise. But you're like, all right, we have an infinite number of time segments here, but the time segments then keep getting smaller and smaller and smaller, and they get infinitely small. And the answer is obvious that, okay, we can outrun this tortoise, but how do we mathematically reconcile that with ourselves, that we have an infinite number of time periods, but they keep getting infinitely small? Which one's bigger? Which is it, infinite number of time periods bigger, or is it the amount of time that each time period has? And so without limits, or the idea of limits, we really can't compare these two. And that's why it's referred to as Zenos Paradox. He did a handful of, fables, which kind of address this concept here. So then, this brings us to the concept of indeterminate forms. So we have a handful of indeterminate forms. If you get something in the form of 0 over 0, or infinity over infinity, then you're kind of like, well, or, let's do another one, infinity times 0. The idea here is this 0 smaller than that 0? Does this equal 1? Does this equal 0? Because if this 0 is really, really small, but this is kind of a bigger 0, then you have 0 over something kind of sort of big, which then just becomes 0. Because 0 over anything is 0. Unless, of course, that's 0. In which case, you really don't know. And these are called indeterminate forms. These are the ones that we will work with for the most part. But there's lots of others. You can get things like 1 to the infinity, infinity minus infinity. You can get these sort of things too. And those are all indeterminate forms as well. But, or 0 to the infinity? Probably. I think so. Or maybe infinity to the 0. Interesting. Because 0 to everything becomes 1. But long story short, don't get too sidetracked. These are the kinds that we'll normally see. Let's look at another example of an indeterminate form just to get the concept right. You might be like, you're spending so much time on the concept, just tell me how to do this. Yes. Limits are actually surprisingly important in calculus. You'll see them a few times. So you see them now, where it's kind of like, okay, limits. Then you'll see them later, after we've done derivatives, and then we'll see them again when we do series. I know we haven't talked about actually what derivatives are yet, let alone what series are, which have to do with integrals in the area under the curve. But this concept keeps coming back. So the better idea you have of the grounding, the basic concept of it, the easier it is to kind of churn through these problems. And these tend to be more conceptually based problems. So we're going to go to another example called Pascal's Wager. So Pascal's Wager is something along the lines of, all right, there's two things that can happen in life. So there is a God, we'll call that a probability P, or there isn't a God, which would be probability of 100% minus whatever P is. And the eternal happiness, bliss that you get from there being a God and you believing in God is, well, you get to go to heaven, which is infinitely good. Or it turns out that there is no, I'll leave that P out for now. Turns out there is no God and you die and this kind of things go away. Kind of the whole atheist idea of, well, there is no God, you die, it's just like before you were born, therefore it's not good nor bad, you just kind of 0. Doesn't matter. And so then when you run the probabilities here, the probability of there being a God multiplied by the amount of happiness you have is p times infinity, because infinite happiness. And then you would add in the probability of there being no God or no heaven or whatnot times 0, no additional happiness. And this would be your expected net happiness in life. Well, death? In death? I don't know. I guess there's probably a lot of value for religion when you're alive, but we're just looking strictly at the afterlife here. And so Pascal is basically along the lines of, well, it doesn't matter how small this p is, how unlikely there is that God exists, because you're rewarded with infinite happiness. And if you're rewarded with infinite happiness, then no matter how small the likelihood of God existing is, it's still worth the effort to be observant and believe in God, because infinity times anything will be infinity. So if this, there's only like a 10% chance that God exists, it's totally overpowered by the fact that it's an infinite happiness. So you should totally believe in God just to kind of hedge your bets here. And so he's like, well, this is infinity. Well, this kind of becomes an indeterminate form. So the no God, this part, it's like, well, it doesn't matter because it's multiplied by 0. We're going to go with that for now. But you have this other form here, the probability of God existing times infinity. And when he says it doesn't matter how unlikely God is, there's always going to be the chance that he is there. And if that p probability exists, you multiply it by infinite happiness, totally worth your time to invest in believing in God. And so this is the same form here as infinity times 0. Now if you look at infinity times 0, that is kind of sort of the same form as infinity over infinity. Because if you divide something by infinity, that's kind of the same as multiplying it by 0. Again, back to algebra. So the idea with this Pascal's wager here is, with this part here, this, even if it's 0, basically 0, and you have infinity here, this is a form where it's basically indeterminate. And that's kind of the idea that Pascal is playing with here, is it's really hard for us to conceptually understand the grandeur of infinity when we multiply it by 0. And this was the whole idea behind Pascal's wager, is playing on the difficulty of the human mind to conceptually grasp something that's absolutely 0 and something that's infinite. And that's kind of the idea where it comes down to limits. Now, granted, it's really hard to quantify what the percentage chance of God existing is, which is why this really can't be resolved. On a more intuitive, common sense day-to-day occurrence, we see the same phenomenon here with the actual lottery, where you see win but with some small probability of winning, some probability of losing, which is more likely, probably more likely, and you win, in effect, an infinite amount of money. For the average person, they're like, well, you can win $20 million. It's like, well, as far as I'm concerned, that's an infinite amount of money. That's a lot of money. And you can't imagine or visualize how much money that is. And so intuitively your feelings like, oh, infinite amount of money. Even though your chance of winning is 1 in, 30 billion. Not a good chance of winning. Is that enough zeros? I'll add some more zeros. Very unlikely chance. When you hear this, $20 million, you're like, wow, that's a lot of money. It's of course likely for me to play the game. And people intuitively get lost in this number of zeros, which is why it's difficult and why formalized limits are kind of important to look at. So that's the concept behind limits. That's why limits exist. And that's why it's kind of the philosophical underpinnings of calculus in general. So you take all this, let's look at a slightly different, more condensed way of looking at this. So one more philosophical trip. I know, so many philosophical trips. That the most philosophical part here is going to be in limits, so you're fine. So let's look at 1.99 repeating, basically that little line right there means goes on forever, continue writing 9s forever, does this equal 2? I'm not saying is it close to 2, it's like, is it exactly 2? So if we have 1.99 forever, is that exactly the same as writing 2? And for calculus and limits, the answer is yes. That is exactly the same. If I take 1.9, repeating, writing 9s forever, all eternity, an infinite number of 9s, that is exactly the same as 2. And you might come down philosophically like, I don't know, it's slightly less. Yes, you could say that. But if you do say that, then calculus isn't going to work. So if you want calculus to work, the underlying assumption of calculus is 1.99 repeating forever is exactly 2. And that's the same idea that we're going here with both Zenos Paradox and Pascal's Wager, is the limit as 1.99 forever goes on, that equals 2. So they're like, okay, well, how do we use this? How does this actually apply? What kind of problems can be asked here? Good question. Let's clean up the board here. Whoop. Go through some examples. So I'm going to write up an equation. So you'll see people talk about limits. So we'll say limit, Lim, this is kind of the standard notation, as x approaches -5 of, let's say, x squared minus 25 over x squared plus 2x minus 15. Okay, so talk about this equation, what this setup means real quick. So we have more contrast, purple, green. So we have a function here with x, and we're saying x comes close to -5. And we're like, okay, well, that's pretty easy. Let's plug in -5. So you have -5 squared is 25 minus 25 all over x squared, which is 25, plus -5 times 2, which is -10, minus 15. And that equals, on the top you have 0, and on the bottom you have 0. Indeterminate form. We don't know. And so we're stuck with this issue of like, okay, how do we go from this? And what we do then is we can adjust the equation to basically get more information out of it. Which is bigger, the top or the bottom? And so we're going to rewrite this a little bit and see if there's another way of looking at this. So you look at the top part and you're like, well, that's a difference of squares. So I'm going to leave off the limit x approaches -5 just for convenience right now as I rewrite things and simplify. But we have x plus 5, x minus 5, difference of squares. And then this, you think we can switch that into 2 binomials. We can defoil it, if you will. If you remember FOIL from algebra, basically first, outside, inner, last. If you do the opposite of that, which is basically done by either inspection or the quadratic formula, then you'd find, okay, so if we do x plus 5, x minus 3, then you see that x squared, you have 5x minus 3x, which is 2x, and then 5 times -3 is -15. Then we get this. Okay, well, we can then cancel the x plus 5s, and we're left with x minus 5 over x minus 3. If we take this and we do limit as x approaches -5, then we have, let's see here, it would be -5 minus 5 over -5 minus 3, which gives us -10 over -8, which gives us 5/4. And so what this is saying here then is x -5, as x approaches -5 for this equation, we're actually going to get the answer of 5/4. And this is not the same, well, yeah. I would say this is the same as 0 over 0, except this is an indeterminate form because it's 0 over 0. It has that limit issue that we talked about. And so we don't actually know what 0 over 0 in this case equals. And so we can find out later through this algebra that this 0 over 0 actually equals 5 over 4. This indeterminate form, this form that we're unable to determine what it is, in this situation, we're able to use some algebra to then turn it into, I guess, what? A determinate form? A determined form? A form that we determine what it is, which is 5/4. And so that's the idea of how we can do limits. Now let's take a look at this graph real quick. And for that, we'll use Wolfram. I love Wolfram. So we have, we'll do a top and a bottom. We'll do an x squared minus 25. Then on bottom we have, what were our two? Do I remember? What were they? It was x squared plus 2x. I think that's 2x. Minus 15. All right, so let's check real quick. X squared plus 2x minus 15. X squared plus 2x minus 15. Okay, excellent. And so we have this graph. Let's do, I don't know, y equals. We'll do a y equals. Everyone likes y equals. I love Wolfram. This is a wonderful gift to humanity. Okay. Ooh. I see what happened. X squared minus 25. Okay. X squared minus 25. There we go. We got something kind of like this. But what we were looking for is x approaches negative 5. So we'll say for negative 6. Let's do negative 6. Negative 6 less than x less than negative 4. So we look at these. Bum, 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 bum. So much suspense. So much suspense. Okay. And we get something kind of like a straight line, kind of not like a straight line. But we're zoomed in over here. And so in this area, this is what the graph looks like. And we had what? Was it 5/4 as our answer? So at negative 5, it gets right about, what is it? 5/4 is 1.25. So 1.25 right here. It makes sense. And if we wanted to be a little bit more exact, we'd say like, I don't know, 5.001 negative 4.999. And so now we're zoomed in even more. And before there's a little bit of curve between negative 4 and negative 6. But now pretty much almost completely a straight line, which is a big deal in calculus. So if we do our dy dx here, we'd actually get pretty accurate the smaller we get. When we look at here, we go to 5, come up to here, which is pretty much the same as everywhere else since it's so small. We have 5/4 again. And so this is what it's telling us, that it's 5/4. Now, one key point to look at here is if you look at the denominator, one of the big things in life is you can't divide by 0. World ends, universe explodes, that sort of thing. So you don't want to divide by 0. And if you plug in negative 5 exactly, then you're basically dividing by 0. So we go back to our equation here. So we have x plus 5, x minus 5, and I can do a better parentheses there. There we go. All over x plus 5. Nope. There we go. X minus 3. And we're doing limit as x approaches negative 5. Oh, clean up the board briefly. Get rid of some of that. We can't actually plug in negative 5. So if we look at our graph, at this section, looks kind of like this, where this is right around negative 5, and this is right around 5/4. And we can't actually plug in negative 5, so there's a hole in this graph right there. Because if we plug in negative 5 here, negative 5 plus 5, that equals 0, divided by 0, world ends. Also, we can't plug in x equals 3 either, but that's way over here, and we're not looking at that right now. So what this graph looks like is something like straight line does not exist, straight line. And that's one of the key ideas of limits, is the point doesn't actually have to exist for the limit to exist. So this, even though this equals 5/4, we can't actually go to 5. So if you're like, well, what is the limit as we get really, really close here? to point to the x equals -5, well, that's going to equal 5/4. But if you try and plug in -5, the graph explodes. So the idea is that point doesn't actually have to exist for its limit to exist, which is one of the nice things about limits is you don't actually have to be at the point, you just have to get close to the point. And that's one of the ideas, key concepts here with limits is the point doesn't actually have to exist, you just have to get close to the point. And that's what's going on right here. So let's look at another example to illustrate kind of one of the other points that we use here. So if we have this equation up here, we have limit as x approaches infinity. Before we had a specific point that we were going towards. This is what happens when it goes to infinity. And we have x squared plus 2x plus 2 on top, and then 2x squared plus 3x on the bottom. And you're like, well, if you have x squared on the top, that's infinity squared, and that's going to be infinitely big. But then we also have 2x squared on the bottom, which will be dividing by infinity squared, which will be infinitely small. And it's like, well, which one is bigger, and how do we reason our way through that? So this is a kind of problem you'll see from time to time in life. And the way you generally approach it, I'm not going to rewrite the limit x approaches infinity again. It should be there, but for convenience, I'm leaving it off. One way to look at this is you factor out the x squared on top, and you get 1 plus 2 over x plus 2 over x squared. I shouldn't have a curly bracket and a square bracket. There we go. So then we have, factor out the x squared on the bottom, and we have 2 plus 3 over x. And then when we put in infinity, we can see that, well, for starters, we'll look at the x squareds and be like, okay, the x squareds go away. 2 over infinity, well, that's going to be 0. 2 over infinity squared, that's also going to be 0. And then 3 over infinity, that'll be 0. So this, in the end, we're just left with 1/2. So the limit as x approaches infinity of x squared plus 2x plus 2 over 2x squared plus 3x will only be 1/2. So looking at Wolfram, let's see, x squared plus 2x plus 2. So we have x squared plus 2x plus 2 divided by quantity 2x squared plus 3. 2x squared plus 3. We look at this as a graph. And as x gets super, super big, we'll assume it approaches 1/2. So you can see this goes all the way up to 40. So, yeah, okay. Let's do something bigger then. 0 less than x less than 200. Bum, bum, bum. No, that looks like 4. That way it knows we're talking about the domain. Bum, bum, bum. And you see as it goes way out, it's getting closer to 1/2. So right here, we have a horizontal asymptote, where as x approaches infinity, we get y approaches 1/2, which kind of seems reasonable. And that's kind of another form that you'll see with these idea you'll see with these limits. And so the idea of factoring out the x squared and canceling it and being left with some constant over infinity is kind of a common, not trick, I don't like the word trick, but a technique that you'll use from time to time. Okay, so now let's look at another graph. So we'll say y, that looks like a 4. I want to do something that's a little bit more inquisitive. So y equals, let's say, absolute value of x. And so when we graph this up, we know what it looks like. We've seen this before. Nothing new to us. So we have something that looks like this, and then we have something that looks like that. So y equals x goes straight, but since you take the absolute value sign, it flips it up. And so that all the values are positive. This will be the x, this will be the y, and what we want to look at is the limit as x approaches 0. Limit as x approaches 0 of the absolute value of x. And so the idea here is, the closer you get to 0, it's just going to be 0. You can put in 0 into the absolute value sign, and it still will give you an answer. And so this has a limit at x equals 0. Would be interesting too, we could even say something like x cannot equal 0. Or for x equals 0, y equals, I don't know, let's say 2. So if there's a hole there, that specifically does not exist. Do it in purple so it's more obvious. And then the point is actually up here. The limit as x approaches 0 would still be 0. It doesn't matter, the point that you're actually talking about doesn't exist. It's all the points leading to that point. So we have something like this where we have a point here, it's pointy, an abrupt change of slope, and let's say the point doesn't even exist there. That's okay. This limit here, the limit is x approaches 0 of absolute value of x, would still be 0. Now one of the important concepts and notations you'll see is, I'll say that limit as x approaches 0 from the left, that's what that little negative sign set means. So it's basically saying that as we're approaching from this direction, the limit looks like it's going to 0 at x equals 0. We'll say that that equals the limit as x approaches 0 from the right, from the positive side, from this direction, that these both equal 0 because they both go towards the same point. And that's required to be able to say that, change back to purple, limit as x approaches 0 equals 0. So the idea here then, for this limit to exist, the limit as, writing right here, limit as x approaches 0, for that to exist, the limit as x approaches from the left, usually denoted by whatever value you're going towards, with a little zero negative sign up here, equals the limit as x approaches 0 from the right, which is denoted by the little plus sign. Those two have to equal each other, which will then, by definition, equal what the limit is. And so these two equal, if someone writes out limit as x approaches 0, that means that that limit as x approaches 0 equals the limit as x approaches 0 from the left, which equals the limit as x approaches 0 from the right, which all have to equal the same thing. For this limit to exist, for this value to exist, right here, this section right here has to be true. And I try not to memorize formulas, but I just kind of look at the graph and be like, okay, coming from the left side has to be equal, coming from the left side has to be equal to coming from the right side. And that has to give us the same value. Now, granted, that doesn't actually have to be where the point actually is. The point can be way up here. But they have to be coming towards a same value. And that's an idea we have for limit as x. Now, to foreshadow a little bit later, we would say that the derivative, which derivative is just another word for the slope, the derivative at 0 does not exist. Because it's a pointy, whenever you get some sort of sharp turn like that, you can't determine what the slope is, because if you look at it, you have two possible answers. One is you have the slope basically approaching from the right, which looks like this. And then you have the slope approaching from the left, that looks like this. And since you have two different slopes, depending on if you approach it from the left, the 0 minus, or from the right, the 0 plus, that means the slope, or the derivative more specifically, does not exist. So the limit here would exist, but the derivative would not exist. Another way of saying it is, this equation is not differentiable, i.e. the derivative does not exist, at x equals 0. So that's the idea. That's one of some of the key takeaways from this graph. So let's look at another example. All right, one more example, kind of to drive the whole idea home. So we have graph, kind of like this. Whoop. Ooh, light blue. So I have, let's do it this way. So we'll go like this, and we'll go like that. So the dot with a hole in it that's empty means no value there. The hole that's filled up means there is a value there. And so we'll say that y equals, let's call that 2 for x greater than or equal to 0. Y equals 1 for x less than 0. And the idea is, what is the limits here? So the limit as x approaches 0 for 0 from the right would equal 2. Because if we're coming in from this side, right along here, that equals 2. But the limit as x approaches from the left, well, that just equals 1. So we come to this side, it equals 1. And so the result here would be limit as x approaches 0 plus does not equal limit as x approaches 0 from the left. Therefore, limit as x approaches 0 as a whole does not exist. And that's a key takeaway here. And your thought process might be like, okay, so that's all good in concept, but how are we going to see this on the advanced placement exam? How's this going to come up? You'll see this a lot in terms of word problems where they're like, hey, what's, does this limit exist? What's the idea behind this? You have this situation, and you have to reason out that, okay, the left side and the right side don't match up, therefore the limit as a whole does not exist. But when it comes to actually, you'll be asked, hey, here's some sort of function, find the limit as this function approaches some number, often 0 or 1 or infinity. And from the couple examples I saw, you're like, oh, it's pretty easy. We'll factor out the x squared, cancel them, and then we get an answer. Or you'll be like, well, we factor the problem, cancel out some things, and then an answer appears. And that's true. You'll rarely see problems like that on the AP exam. So what you'll see more of are things like, let's say, limit as x approaches 0 of x over sine of x. And from the techniques that we've talked about, you have no idea how to do this. You can't factor out x, you can't do anything really. And you plug in 0, you get like, well, 0, sine of 0 is 0, and it's like, well, nothing we can do. Well, we'll talk about a little bit later something called L'Hopital's rule, which basically we'll talk about derivatives, and then we'll come back to limits, and what we'll do is we'll end up taking the derivative of x, we'll take the derivative of sine of x, and then we plug it in again, and we get 1 over 1, which is 1. And if you look at a sine of graph of x over sine of x, nope, not like that, looks kind of something like this. And you'll find that the limit as x approaches 0 is 1. But you don't know how to do that yet because we haven't talked about derivatives. And if you plug in, switch the idea of looking at the slopes of one versus the other, or the rate of change of one versus the other at that point, and that will give you the idea. But that's foreshadowing. This is the idea of limits, and this is the idea of philosophically when we have a graph like such, why we can take the dx, dy, turn that into a slope, dy dx, which then gives us our derivative. And then we can make those as small as we want and look at those as they get infinitely small. So that's the idea and concept behind limits, and we'll use that then to find our derivatives next time. Thanks for stopping by. I will see you guys next time. Thank you much.